Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on control systems theory. Last time we discussed the analysis of control systems in frequency domain, where we discussed the resonance peak, resonance frequency and bandwidth frequency. Today we are going to continue our discussion on frequency domain analysis, but today we are going to study some very special tools in control systems theory, one of the major tools that are used in analysis and design as well. So we are going to study Bode plot and Nyquist plots, and specifically we shall be looking into how to analyze control systems using Bode and Nyquist plots. So the key points that we shall be discussing in this lecture are as follows. First of all, Bode and Nyquist plots are used to analyze the following properties of the control systems. They are used to analyze the closed loop asymptotic stability. You can determine whether the closed loop system is asymptotically stable or not using Bode plot or Nyquist plot. They are also used to determine the gain margin of closed loop systems and phase margin of closed loop systems. So these are the three key properties of control systems that we can study using Bode plot and Nyquist plot. And we sketch the Bode plot. This is very important point, that we sketch the Bode plot and Nyquist plot using the open loop transfer function, and this sketch basically helps us in determining the properties of corresponding closed loop control system. So this is similar to steady state error analysis. So you see that type of a system, when we discussed the steady state error analysis, we saw that the type of the system is determined by open loop transfer function. The number of poles in open loop transfer function at the origin determine the type of the closed loop system. Then similarly we looked at the root locus. We start with the open loop transfer function and we use the rules or 10 rules of root locus and sketch the path of the poles. And similarly here in Bode plot and Nyquist plot, we use the open loop transfer function to determine the properties of the closed loop systems or closed loop transfer functions. So this is one of fairly common things in control systems theory that you should be familiar with by now. So Bode plot is sketched in two parts. First of all, there is a log-log plot of magnitude of the open loop transfer function versus frequency. So in the first part of the Bode plot, you have y-axis and x-axis in logarithmic scale, and usually the log to the base 10 is used, and in logarithmic scale you plot the magnitude of the open loop transfer function versus the frequency. And in the phase plot, the second plot of the Bode diagram or the second Bode plot is the semi-log plot of phase of the open loop transfer function versus frequency. This is semi-log because frequency on x-axis is in logarithmic scale, whereas the phase of the transfer function is in degrees. Usually it is in degrees on y-axis. So that is why so one of the axis is in logarithmic axis, logarithmic scale, and the other axis is not in logarithmic scale. That is why it is called semi-log plot. And we shall be looking at different Bode plots during this lecture, so you will know what I am talking about. Nyquist plot is the plot of real part of the open loop transfer function versus the imaginary part. So in the beginning of this course we discussed that there are two ways to determine the frequency characteristics of a system. One way is to decompose the transfer function into gain and phase, and the other way is to decompose the transfer function into real and imaginary parts. So if you decompose the transfer function into real and imaginary parts and produce a plot of real part versus imaginary part, that is Nyquist plot, and that is used to study closed loop stability, gain margin and phase margin. Whereas if you decompose the transfer function into magnitude and phase, then you get the Bode plot, which is basically a combination of two plots. Sometimes this is called Bode diagram, and this Nyquist is called Nyquist diagram, but it does not matter what word you use as long as you are consistent. Sorry, Bode and Nyquist plots both are used to analyze the closed loop stability, gain margin and phase margin of the closed loop system, whereas both are sketched with the help of open loop transfer function. So we sketch the open loop transfer function real and imaginary parts, or we sketch the gain and phase of open loop transfer function, but those sketches give us the properties of closed loop transfer function or closed loop system. So this is quite interesting. Alright, so let's look at an example. So consider the open loop transfer function g of s into c of s equal 1 over s into s plus 1. So here in this transfer function we have two poles, one at the origin and one at -1. So the open loop system in itself is not asymptotically stable. The corresponding closed loop transfer function, if you use the Mason's rule or block diagram algebra, we have done this many times now, so you should be able to recognize this closed loop transfer function formula, g into c over 1 plus g into c. Then you can see that the denominator is s square plus s plus 1, and if you remember the Routh-Hurwitz criteria for second order system, then you can see all three coefficients are strictly positive, so this closed loop system is asymptotically stable. So this example tells us something, that for the closed loop system to be asymptotically stable, it is not required that the open loop system should also be asymptotically stable. An unstable open loop system can lead to a stable closed loop system, and also a stable closed loop system can lead to an unstable a stable open loop system can lead to an unstable closed loop system. So there is no relation or fixed rule related to the stability, so it is not straightforward to determine the stability of closed loop system from the open loop from the stability of the open loop system. But if you use Nyquist plot or Bode plot, then you can do that. You can determine the stability of closed loop system using the Nyquist plot or Bode plot of the open loop system. So we sketch the Bode and Nyquist plot of Cs into Gs, which is the open loop transfer function, and this provides us information about the properties of the closed loop transfer function. So here is the Bode plot. You can see that Bode plot is composed of two different plots. This is the magnitude in dB. dB is a 20 into log 10. So this is a logarithmic scale. And frequency, you can see 10 raised to the power -2, 10 raised to the power -1, 10 raised to the power 0. So this is in terms of the powers of 10. So this is a logarithmic scale as well. Whereas the phase is in degrees. So this is not a logarithmic scale. So if you consider this versus this, so this is log plot, and if you consider the phase plot, this is the semi-log plot. You can see that the gain of the transfer function or the magnitude of the transfer function starts with the highest value, and if you as you increase the frequency, the gain starts to decrease, and at one frequency it crosses the 0 dB value, and then it keeps on decreasing further on. And this value is important, as we will see in the upcoming slides. This value of frequency at which the gain plot crosses the 0 value, it's called gain crossover frequency, and it is important in determination of phase margin. And similarly, this is a phase plot. Here also the -180 degree value is of certain importance, as we shall see in the upcoming slides. Alright, so next is the Nyquist plot for the same transfer function, and in the Nyquist plot we plot the in the real axis there is a real part of the transfer function, real part of this open loop transfer function, and on the y-axis is the imaginary part of this open loop transfer function. So if you are to find real and imaginary part of a complex number, then what you have to do is replace s with j omega and rationalize the denominator. then you can separate out the terms with j and the terms without j, and then for different values of omega you get different points on this plot, and when you join all the points together, then this would be the Nyquist plot for positive frequencies, and the mirror plot is the Nyquist plot for negative frequencies. Usually in control systems we ignore this mirror part, the negative frequencies part. We only consider the positive frequency Nyquist plot, but it does not matter much. So nowadays in 21st century you have many softwares that can sketch the Nyquist plot for you, and also the negative frequency part is always mirror image of the positive frequency part. As you can see that the plot below this real axis is same as the plot above the real axis. So this Nyquist plot also gives us certain information like closed loop stability, phase margin and gain margin, as we shall see in the upcoming slides. But for now you just have to get yourself familiarized with the concept of Nyquist plot and Bode plot. In Bode plot we have the sketch of gain versus phase. So gain is the real part square plus imaginary part square whole under root, and phase is tangent inverse imaginary over real part. So in a way Nyquist and Bode plots are related with each other. In the old days people were able to construct a Bode plot using the Nyquist plot and vice versa, but I think in the 21st century this skill may not be in high demand. But it's the deeper the stronger your concepts, the better control system engineer you will become. So I never discourage you from learning more than what I cover in the lecture. So determination of next we discuss the determination of closed loop stability from the Bode plot. In order to determine the closed loop stability from the Bode plot, you have to understand the two concepts which are the gain crossover frequency. The first of the two concept is the concept of gain crossover frequency. The frequency at which Bode magnitude or gain plot crosses the zero, as I said earlier in the previous slide. This is the gain crossover frequency, and usually you can denote it by omega sub gc, omega gain crossover. So this is the frequency at which Bode plot crosses the magnitude, Bode plot crosses the 0 dB value. And then there is a frequency at which Bode phase plot crosses minus 180 degree value. This is called phase crossover frequency or omega phase crossover, omega sub pc. And now once you understand phase crossover and gain crossover frequency, then closed loop system, the stability, asymptotic stability of the closed loop system is guaranteed if in the Bode plot of the open loop transfer function you have omega gain crossover less than omega phase crossover. So this means that you just look at the Bode plot, and if you see that the gain crossover frequency is smaller than the phase crossover frequency, which means that the gain will cross zero sooner than the phase, then it means that the closed loop system corresponding to that Bode plot will be asymptotically stable. Remember that the Bode plot is sketched for the open loop transfer function, and this property has to be satisfied for the Bode plot of open loop transfer function. But if this property is satisfied, then you conclude the asymptotic stability of the closed loop transfer function. So this you always have to remember. So we look at this Bode plot, and you see that this gain is crossing 0 dB at the frequency which is slightly less than 1 radian per second. It is somewhere between 0.1 and 1 radian per second, and at this frequency the phase has still not crossed minus 180 degree. So in this example you can see gain crossover frequency is slightly less than 1, but the phase crossover frequency, if you keep on sketching this plot, so phase crossover frequency almost, it is very high. It will almost go to infinity, because this phase will asymptotically be converging to the value of minus 180 degree, but it will never cross the value. So as long as it never crosses the value of minus 180 degree, then phase crossover frequency in this case is infinite. So phase crossover frequency is infinite, gain crossover frequency is a little less than 1, which means that gain crossover frequency is definitely less than the phase crossover frequency, which means that the closed loop system corresponding to this Bode plot, the closed loop system corresponding to the open loop system for which the Bode plot has been sketched, that closed loop system will be asymptotically stable. So this is how you determine asymptotic stability from the Bode plot. You just look at the gain crossover frequency and phase crossover frequency. If phase is crossing 180, minus 180 after the gain has crossed 0 point, then it means the closed loop system will be asymptotically stable. Similarly, there are ways to determine gain and phase margin from the Bode plot. It's basically quite easy. Phase margin of the closed loop system is the difference between the phase of the open loop transfer function from minus 180 degrees at the gain crossover frequency. So this means that at the frequency where the gain is crossing 0, you look at the phase. So when you look at the phase at gain crossover frequency, if this phase is let's say greater than minus 180, let's suppose it is minus 120, then the phase margin will be 60 degrees, because there is a 60 degree difference between minus 120 and minus 180. Phase margin will always be almost always be positive. If phase margin turns out to be negative, then it means that closed loop system is not asymptotically stable. Or on the other hand, it is quite possible that the phase of the system may be I wouldn't say rule out any possibility, because there could be many different types of systems having zeros and poles at different frequencies, and maybe there is a case where the phase is even greater than 0, but phase margin, the maximum limit of phase margin is 180 degree. So phase margin is ranges between 0 and 180 degrees. Then gain margin of the closed loop system is the negative of the gain of open loop transfer function at phase crossover frequency. So in order to determine the phase margin, you look at the gain crossover frequency, and in order to determine the gain margin, you look at the phase crossover frequency. And at the value of phase crossover frequency, you look at the gain. If the gain is already negative, then it means that the closed loop system is asymptotically stable and there is some positive gain margin. If the gain at the phase crossover frequency is still positive, then that means that the closed loop system will be unstable and there is no purpose of trying to determine the gain margin, because gain and phase margins by definition are the tolerance values against disturbances without losing the stability. So we look at the Bode plot. You can see here that this is the gain crossover frequency. We add the gain crossover frequency, we look at the phase of the system, and you see that here gain crossover frequency is 0.786 radian per second, and at gain crossover frequency phase margin is 51.8 degrees. So there is a 51.8 degree difference between the phase at gain crossover frequency and minus 180 degrees. Alright, so next we look at the phase crossover frequency, and you can see, as we discussed earlier, the phase crossover frequency in this case would be infinity, as it is written here. So phase crossover frequency is infinite radian per second. So as this goes to infinity, you can see that the gain is constantly decreasing and the gain is going towards minus infinity, and negative of the gain at infinite frequency, that will be plus infinity. So the gain margin in this case is infinite. So there is infinite gain margin because the phase crossover frequency is infinite, and there is 51.8 degrees phase margin. So infinite gain margin because the phase crossover frequency is infinite, and 51.8 degree phase margin because 0.786 gain crossover frequency. So we find the phase margin at gain crossover frequency and gain margin at phase crossover frequency. So this completes the analysis using the Bode plot. We now know how to determine the closed loop stability and how to determine the gain margin and phase margin of the closed loop system. Once again, I just want to repeat here that gain margin is the ability of the closed loop system to tolerate the disturbance of certain gain without losing the stability. So if gain margin is 30 dBs, that means that any disturbance within 30 dB magnitude or within 30 dB gain cannot make the closed loop system lose its stability property. If the disturbance goes larger than the gain margin, then that disturbance may cause instability in the closed loop system. Similarly, phase margin is the tolerance against the delays in time domain or phase difference in frequency domain before losing the asymptotic stability property. Next we look at another transfer function. So this is a third order transfer function, 1 over s cube plus 2s square plus 3s plus 1. So this is open loop transfer function. The corresponding closed loop transfer function will also be third order, but we sketch the Bode diagram for this transfer function, and you can see here that for this transfer function, first of all look at the gain and phase crossover frequencies. So this is basically the phase crossover frequency. At this frequency the phase is crossing minus 180 degrees, and if you look at the gain starts at 0. So gain actually never crosses 0. So gain crossover frequency is you can see that there is no gain crossover frequency, or at the most you can say that gain crossover frequency is 0 radians per second. So if gain crossover frequency is 0 radian per second, at the 0 radian per second the phase is 0 degrees, which means the difference between the phase and minus 180 degree is 180 degrees. So phase margin is maximum possible phase margin, which is 180 degrees. Usually we do not write the negative sign in front of phase margin. Phase margins are positive. And then gain margin is determined at the phase crossover frequency. So at the phase crossover frequency the gain is minus 14 dB. So this is minus 14 dB. So the negative of the minus 14 dB is plus 14 dB. So the gain margin would be plus 14 dB, which is the negative of the value of gain in dBs at phase crossover frequency. Similarly, since the gain crossover frequency is less than the phase crossover frequency, so we do have closed loop stability in this case, and you can calculate the closed loop transfer function and apply Routh-Hurwitz and verify that indeed the closed loop system would be asymptotically stable. Next we move on to Nyquist plot, and first of all we try to determine how to calculate or analyze stability of closed loop system from the Nyquist plot. In order to do that, first of all you have to see, let the number of open right half plane poles in the open loop transfer function be P. So let us assume that you have an open loop transfer function and there are some poles in the open loop transfer function. Some of them are in the right half plane and some of them are in the left half plane, and some of them are on the j omega axis. So the poles on the right half plane excluding j omega axis, that the number of poles on the right half plane of the open loop transfer function is P. So if you determine the open right half plane poles of the open loop transfer function by P, and then let the number of counterclockwise encirclements of the point minus 1 by the Nyquist plot of open loop transfer function be N. So you look at the Nyquist plot of the open loop transfer function, and there is a minus 1 point on this plot. Minus 1 means the minus 1 point on the x-axis or the minus 1 point on the real axis. So if the Nyquist plot is encircling this minus 1 point counterclockwise, if the Nyquist plot is encircling this minus 1 point counterclockwise, then the number of encirclement is denoted by n. And then in order to find the closed loop system stability, you compare number of p with the number n. If n is equal to p, then your closed loop system is asymptotically stable. If n is greater than or less than p, then your closed loop system will not be asymptotically stable. So the remark is that the stability property of the open loop and closed loop systems may or may not be same. So which we already know, because an unstable open loop system may lead to an asymptotically stable closed loop system, and similarly asymptotically stable open loop system may lead to an unstable closed loop system. So this is how you determine the stability from the Nyquist plot. You count the number of encirclements by the Nyquist plot of the -1 point, and then you count the number of open right half plane poles in the open loop transfer function. Then you compare the two numbers. If they are exactly the same, then you conclude that the closed loop transfer function is asymptotically stable. Now we look at an example. This is the Nyquist plot of some transfer function, and this is the transfer function. The open loop transfer function is s plus 2 over s square minus 1. The open loop poles are -1 and +1. So you can see that there is a one right half plane pole in the open loop transfer function. So p is equal to 1 in this case. And then this is the -1 point. This red plus sign, this is the -1 point. And this is the Nyquist plot. So you can see the Nyquist plot is encircling the -1 point one time. So this number of encirclements is 1. So n is equal to 1, and here p is equal to 1. So since n and p are both 1, this means n is equal to p, and this means that the closed loop system corresponding to this Nyquist plot will be asymptotically stable. Although the open loop system is unstable, the corresponding closed loop system will be asymptotically stable, as we have determined from the Nyquist plot. Similarly, look at another Nyquist plot. Here this is the -1 point, and you can see that there are no encirclements of -1 point by the Nyquist plot. So n in this case is equal to 0, and this is the transfer function corresponding to which this plot has been sketched. And you can see here that in this open loop transfer function, there are two poles at -0.78 plus -1.31 iota and -0.43. All of these poles are in left half plane. So number of poles in the open right half plane is 0. So since p is equal to 0 and n is equal to 0, n is equal to p. So this means that number of encirclement is equal to number of right half plane poles. So this means that the closed loop system corresponding to this Nyquist plot will also be asymptotically stable. So in this case, the open loop system itself is asymptotically stable, and it leads to closed loop system which is also asymptotically stable. And in this case, open loop system is unstable, but it leads to a closed loop system which is asymptotically stable. Alright, so next we look at how to determine the gain and phase margin from the Nyquist plot. So let alpha be the point between 0 and -1 on the real axis, where the Nyquist plot of the open loop transfer function crosses the real axis. Then the gain margin of the corresponding closed loop system is absolute value of 1 over alpha. So this is how you determine the gain margin from the Nyquist plot. You look at the you look at the crossing of the Nyquist plot, of the real axis crossing the x-axis crossing of the Nyquist plot on the negative side on the left half plane, and if there is a crossing at some point alpha, then the absolute value of 1 over alpha, that will be gain margin. For example, if there is a crossing at -0.1, then the gain margin will be 1 over 0.1, which will be 10. So if the zero crossing is at -0.5, then the gain margin will be 1 over 0.5, which will be 2. So similarly, you keep going. If the crossing is at 0, then gain margin will be 1 over 0, which is infinite. And if the crossing is at -1, then the gain margin will be 1 over minus 1, which is 1. Okay, so consider the point on the Nyquist plot of the open loop transfer function where the Nyquist plot crosses the unit circle. So in order to determine the phase margin using the Nyquist plot, you have to sketch a unit circle centered at the origin. And once you sketch the unit circle centered at the origin, then you have to see where the Nyquist plot intersects with this unit circle. And the point where this Nyquist plot intersects the unit circle, then you draw a vector from the point of intersection of Nyquist plot and the unit circle to from the origin of the frame, from the 0 point to the point where Nyquist plot is intersecting the unit circle, and that vector will be vector OA, and you draw the vector from origin O to the point A, and the angle between the vector OA and negative real axis is the phase margin of the corresponding closed loop system. So in order to determine the phase margin, you have to sketch the unit circle and look at the look at the crossing of the Nyquist plot with the unit circle, and you draw the vector OA at that point, and the angle of that vector with negative real axis is the phase margin. So this is how. Now let us look at the example. So this is the Nyquist plot that we are already familiar with, and now let us see how we determine the gain and phase margin. You can see here that the crossing of if you look between 0 and minus 1, the crossing of the Nyquist plot is at the point 0. So 1 over 0, the gain margin will be infinite in this case. Or in other words, some people also determine gain margin in the negative sense. For example, you know that we need one encirclement of minus 1 point by the Nyquist plot if we are to balance this pole at the open right half plane with the number of encirclements. So if you decrease the gain, of this system, then this plot will shrink, and substantial decrease in the gain will cause this plot to shrink in such a way that it will no longer be encircling the minus 1 point. So I will not go into the negative gain margins or negative, but I just want to let you know that there are some concepts where people try to study that if we reduce the gain of the system, then it can also lose stability. But if you increase the gain of the system, even if you increase the gain of the system by infinite times or infinite magnitude, the system is never going to lose the stability. The only way for this system to lose stability if you reduce the gain. And similarly, then there is a phase margin. For phase margin, we have to sketch the unit circle. So here I sketch the unit circle. This is the circle of radius 1, and it is centered at the origin. And you can see that here at this point, the Nyquist plot is crossing or intersecting the unit circle. If I draw the vector from the origin to this point of intersection, then the angle between this vector and the negative real axis, this angle would be phase margin. So in this case, it seems that it is about 40-50 degrees. And then you look at one more example. You have a Nyquist plot of this transfer function. We have already looked at it. You can see here that the crossing with the negative real axis is at maybe minus 0.2. So 1 over 0.2 would be approximately, gain margin will be approximately 5 dBs. Not in dBs, but it will be 5, gain margin will be 5. Okay. Then you have to look at the phase margin. In order to look at the phase margin, you have to draw the unit circle, and this is the unit circle, the circle with radius 1, I think I have sketched the circle with radius. Okay, yes. Let me see. Yeah, this circle has a radius of 0.5, so this is the wrong circle. You can imagine a circle of radius 1. Here again this circle is not alright, so this is the circle. Actually these axes of the Nyquist plot are not of same scaling. So this distance is -2 to 0.5. This is 2.5 distance, and this distance is -0.5 to 0.5, which is 1. So that is why I have been tricked by this unequal axis. And this circle, although this circle is not very appropriate, but it still gives you the right concept that there will be a unit circle, and then you have to look at the intersection, and the angle between this vector and the negative real axis would be the Nyquist plot. And similarly, imagine this unit circle to be this circle to be a unit circle, and the intersection of Nyquist plot with the unit circle, that will basically this vector, the angle between this vector and the negative real axis, that will be the phase margin. So the demonstration of the concept is right in this example, in these examples, but the sizes of these unit circles are not appropriate, and I apologize for that. Hopefully that will not be an obstacle in the way of learning the concept of how to find the phase margin. Okay, so then in the end I want to introduce you to some useful MATLAB commands that I have used for this lecture, and some other MATLAB commands. So there is a command in MATLAB, Bode, BODE, and you in the argument of this command you provide the MATLAB open loop transfer function, and then this will give you the Bode plot of the open loop transfer function, and you can use that to determine the gain, phase margin and stability of closed loop system. Next we look at the margin command. So margin command is very similar to Bode command, but the added advantage of margin command is that it does not just give you the Bode plot, it also gives you the gain and phase margin and gain crossover and phase crossover frequency for the system. Similarly, there is a Nyquist command in MATLAB. So if you use the Nyquist command, it provides you the Nyquist plot for the open loop transfer function, which you can use to determine the gain margin, phase margin and stability property of the closed loop transfer function. Then there is R locus command, which you can use to sketch the root locus. And then there is step command. This command you can use to find the step response of closed loop transfer function, and usually the transfer function you plug in here is the closed loop transfer function. And then similarly there is a step info command. It provides you different information related to the step response of a transfer function. So usually you use in the argument you use the closed loop transfer function. So these are a few commands in MATLAB that are very relevant to what we have studied in this course. And that's the end of today's lecture. And before I conclude everything, I will just briefly revise today's lecture, and we'll see what we have gone through in this lecture. So we started with the key points which involve Bode and Nyquist plot are used to analyze closed loop asymptotic stability, gain margin and phase margin. And I pointed out that we sketch the Bode and Nyquist plot for open loop transfer functions, but they are used to determine the properties of the closed loop systems. Bode is sketched in two parts, log and semi-log plots. Log plots for magnitude, semi-log plots for phase. Nyquist is a single plot between the real part and imaginary part of the open loop transfer function. And we looked at the examples of Nyquist and Bode plots. Here is the Bode plot and here is the Nyquist plot corresponding to this open loop transfer function, which leads to a an asymptotically stable closed loop transfer function. Then we looked at how to determine the closed loop stability from the Bode plot, and all we need to see is whether or not the gain crossover frequency is less than phase crossover frequency. And we look at the Bode plot. If the gain crossover frequency is less than the phase crossover frequency, then the closed loop system would be asymptotically stable. Gain margin and phase margin. So gain margin is determined at the phase crossover frequency, and phase margin is determined at the gain crossover frequency. At gain crossover frequency, the difference between the phase and minus 180 degrees, that difference is the phase margin. In this case it was 51.8 degrees. And at phase crossover frequency, the negative of the gain would be the gain margin. So in this case the frequency keeps on going, so phase crossover frequency is infinite, so negative of the negative infinity would be positive infinity, so gain margin would be infinite positively in this case. So similarly here you can see another example where gain margin is not infinite because phase crossover frequency is not infinite. The phase crossover frequency is basically 1.73 radian per second, and at that point the gain is at minus 14 dB, so gain margin will be the negative of that, which is plus 14 dB. Similarly phase margin in this case would be 180 degrees. And determination of stability from Nyquist plot, you count the number of open right half plane poles of the open loop transfer function, you count the number of encirclements of -1 point by the Nyquist plot of open loop transfer function, and if these two variables are equal to each other, then we conclude that the closed loop system is asymptotically stable. And here is an example where we have one open loop right half plane pole and one encirclement, so closed loop system would be asymptotically stable. Another example where there is no open right half plane pole and no encirclement, so say still the closed loop system would be asymptotically stable. Then we went on how to determine the gain margin and phase margin from Nyquist plot. Gain margin is quite straightforward, but phase margin is a little bit complicated, where you have to sketch the unit circle and look at the intersection of Nyquist plot with the unit circle, and then take the angle from negative x-axis like this. And once again I apologize for the wrong size of the circles here, but hopefully the demonstration of the concept is correct. So you can determine the phase margin using this concept by drawing or sketching the appropriate size of unit circles. Then I went through some MATLAB commands which you can find useful in control systems analysis and design. And thank you so much for listening. Let me know if you have any questions, and I will see you next time. Thank you.